Good morning, my name is Dr. Mark Taylor. I'm a lecturer in railway engineering and civil engineering. Today I'm at Slateford railway station, and what we're going to look at today is the design of stations, platforms, gauging of structures, and we're going to have a close look at the junction that takes the main line here onto the Edinburgh suburban freight line. And in particular we'll look at the signalling on the approach to the junction and the switches and crossings at the junction. Slateford Station is located southwest of the city centre of Edinburgh, and it's on what railway engineers refer to as the Shotts line. And this railway line travels through to the west of Scotland, eventually to Glasgow city centre, and terminates at Glasgow Central Station. This map shows Slateford Station in the red rectangle at the bottom left hand side of the screen. It shows the line passing Slateford Yard and eventually travelling on to Haymarket Junction and onto Haymarket Station. Today we're going to look at the junction at Slateford Station, which connects the line via the Craiglockhart Junction to the Edinburgh suburban line, which is commonly used for freight movements and for bypassing the city centre. So this is Slateford Station, showing platforms 1 and 2. You can see the overhead line electrification, lighting, CCTV, signage, grip bin for the winter months, the overbridge for pedestrians, an emergency phone, a platform gauge is used to help set the platform coping stones to the track. It achieves this by measuring both the height and the distance from the outside rail running edge on a level between both rails. It can be used to both set the platform stones or check and measure their actual dimensions. The platform gauge is both rigid and stable, whilst light and manageable as possible. It has handles and is balanced to enable one person to manoeuvre and operate it, with clear, simple and precise ruler settings. The gauge can be used with no fear of making electrical signalling contact between the two rails, so it will not affect any signalling equipment. You can see the track construction. They're using concrete sleepers here with fast clips. In the next couple of videos, I'm going to show you how the fast clips are constructed and also give you an example of a machine that could be used to install them on site. Note that the video of the machine is using steel sleepers rather than concrete sleepers. The principle is similar. Here you can see a drawing showing the layout of the signalling at Slateford Station, Slateford Junction, part of Slateford Yard, and then eventually Craiglockhart Junction, and then the site of the Craiglockhart Tunnel and the old Craiglockhart Station. If we go back to the top right and we look just to the left of the signal, we'll see a grey box with the numbers 249B, and this is the first of the S&C units that allows the trains to pass over onto the wrong side of the track via 249A, past the ground signal EAS 977, and then through S&C unit 248 across Slateford Junction. So I've just rotated the image, and if you look down at the bottom left, the train's approaching the junction, go past signal ES687. They then cross over to run on the wrong side of the track past the ground position signal ES977, which shows the direction of that ground signal, which is across S&C unit 248 across Slateford Junction. So here you can see the ground position light signal ES977, and this is what it looks like in real life. The arrow indicates the line to which the signal applies. To the right of the S&C unit as well, there's a permanent speed restriction on the diverging route, and that's shown as 20 miles per hour, and the arrow indicates the route. So now we can see that the ground position signal has changed colours, from the two red lights at the bottom to the two white lights showing the direction of travel. The small white plate on the brickwork on the platform edge is referred to as a datum plate, and this gives the design position of the nearest rail to the structure that it's fixed to, in this case the platform edge. And this is to ensure that at the completion of any work that can alter the track position, the information is available to enable it to be left as per the design and not result in the structure being hit by a train. The measurement is taken from the top face of the red block, which is adjustable. The number 11 refers to the individual datum plate number, the 1081 refers to the distance of the structure from the nearest running edge, measured from the top of the red block. The DN is an abbreviation for down, which is the line adjacent. The 0 refers to cant, and in this case there is no cant. This datum plate is not from the location we're looking at today. It's just a picture I got off the internet which shows an example of one. So this is number 13, the offset is 1443 millimeters, and the cant is 10 millimeters. This is a switch plate lubricator. Maintaining smooth switch performance is key to the safe and efficient operation of any rail system. High frequency use, coupled with wear and tear caused by mechanical movement, means that a specialist switch plate lubrication is essential. So as we walk up the track here, we can see the first ground position signal. If you look down at the bottom left, you'll see the lubricator. Then we can see the motor, the heater, the switch rails, the check rails, the stretcher bars and the rods. And again, there's the clear lubricator. The images shown here show S&C unit 248 close up, and what I've done is just annotate some of the major components to help you identify these when eventually you're on site and help you with your terminology. I've also now included a short video from Network Rail which helps explain the various components of an S&C unit and how they operate and why we need them on the railways.
Switches and crossings play an essential role in connecting the rail network. We use them to guide trains from one track to another and to enable lines to cross paths. Put simply, they're the junctions that allow us to create a multi-lined, multi-routed rail network. At Network Rail, we own over 20,000 switch and crossing units. They come in many different shapes and sizes, and all are made to measure for their specific location. To understand how switches and crossings work, we first got to look at the wheel-rail interaction. Train wheels move along the rails guided only by the pound coin-sized area of wheel that sits on the railhead. The wheel rim, or flange, doesn't normally touch the rail. Flanges are only a last resort to prevent the wheels becoming derailed. A switch can guide a wheel in one of two directions. A crossing creates a gap in the rail for the flange to pass through. This is a switch. Also known as a point, it's the moving part of the switch and crossing layout, and is made up of two long blades which can move across to guide the train one way or another. This is the switch rail, and this is called the toe. This is called the stock rail. It's a non-moving part of the switch. The two switch blades are fixed to each other by a stretcher bar to ensure that when one is against its stock rail, the other is fully clear and will provide room for the wheel flange to pass through cleanly. This is a crossing. It's the non-moving part of the switch and crossing layout that allows a train to pass in either direction once the switch has been set. This is the nose of the crossing. Either side of the crossing area, wing and check rails are provided to assist the guidance of the wheel sets through the crossing. Crossings can be either fabricated, made up of two machined rails joined together, or they can be cast as a single unit. Modern crossings are now cast from manganese steel, which is an advanced alloy that gets harder with use. This is an important property, as the nose of the crossing can take high impact loads as train wheels pass through.
My name's Lawrence Walton and I'm a graduate engineer working for Network Rail. I'm here today to teach you about switches and crossings.
The most simple form of S&C is the turnout. This is a left-hand turnout. As you can see, it diverges from the main route in a leftward direction. This is how it works. In normal mode, the left-hand wheel rolls along the switch rail, and there's flangeway clearance for the right wheel to continue along the stock rail. The inside surface of the right flange is kept on course by the check rail. This restrains the wheel set and ensures it is directed along the correct route. Meanwhile, the left wheel transfers contact between the different parts of the crossing. That's where there's a high impact load. In the reverse, the right wheel rolls over the switch rail and follows its geometry. The inside surface of the left flange is guided by the check, forcing it to follow the stock rail on the new route. And the right-hand wheel makes a crossing, again impacting a load on the crossing nose.
There are many different types of switch and crossing on the network. They include turnouts, diamonds, crossovers, and slit diamonds. The type we use is determined by a number of factors, including the number of lines involved, frequency of use, and running line speed. Trains travelling at high speeds need long switches and crossings. At low speeds, such as in stations, trains can make tighter turns. Train movements across the network are set and controlled by signallers, who use switches to set routes for trains. Switches can be propelled by various devices. One of the simplest forms is the ground frame setup, a series of rods and cams attached to levers in signal boxes. These are now largely being replaced by remotely operated hydraulic and electromechanical devices.
Seen by rail sides all across the country. This is an HW2000 points machine. This is electromechanical. What we have here is your drive motor. To check the motor has done its job, over here we have an interlocking and detection system. Detection tells us when the points have completed their travel and locked. Locking holds the points in this state so they cannot be physically moved, so when a train runs over the top it remains in position. Facing point locks are one of the most important safety features on the S&C layout. They ensure that the points cannot be moved when set. This is important because failure to lock the switches could cause a derailment.
As engineers, we face an ongoing challenge to maintain and improve our switch and crossing assets. Trains can create large impact and lateral forces as they change course, and these forces can cause wear and deformation. Switches and crossings therefore have a limited lifespan before we need to replace them. Less than 5% of track miles are made up of switches and crossings, but over 17% of our maintenance budget is spent on them. We'll continue to research and develop new inspection techniques and material usage to increase their performance.
So now we're going to watch a Class 66 locomotive as it crosses over S&C Unit 249B, then on to 249A. It's passing along platform 1. Note that it's running in the wrong direction now. The lights are flickering just because my camera is picking up the frequency of the lights. The naked eye wouldn't normally see this. So now we're going to pass over S&C Unit 248, adhering to the speed restriction. And did you note the ground signal changing as the locomotive passed over? So let's have another look at that from platform 2. So now we'll see a freight train pulling cement, crosses over 249B, across 249A, and we can see there's a divergent speed restriction there of 30 miles an hour. The object in the middle of the track is part of a bridge. And the road passes underneath. There you can see the rear of the ground signal, and again the train's running in the wrong direction. And now it's running over S&C Unit 248. And it's going to pass down the line towards Craiglocker Junction, past Slateford Yard. There you can see another 20 miles per hour speed restriction sign. And you can also see the rear of the 4-aspect signal with route indicator facing the opposite direction to the normal direction of travel. So that's the end of this short lecture, and by now you should have a good understanding of how we construct platforms, how we construct S&C units, some of the terminology, and also you've got an understanding of some of the signalling, which allows, in this case, wrong line running, and also provides speed restrictions as we cross S&C units at junctions. If you get a chance, go down to Slateford Station and have a look for yourself. There's a good overbridge, and you can stand on the top of that and get an excellent view of all the equipment and line-side equipment at the station and the junctions.